So, how many participants are there right now? Looks like about 5. Um,
11, sir.
Sorry?
11.
Oh, 11. Okay. Why don't I see them here on my screen?
Sir, we are streaming it to YouTube, sir. So we the organizers and HOD ma'am and yourself only in the Google Meet.
Oh, I see.
We are streaming this Google Meet screen to YouTube.
I see. Oh, because Google Meet, it being streamed to YouTube. I see. I think probably Zoom has the feature for only sharing for one particular app. See, when I'm presenting, I wanted to have the feature to only present one particular window. Let me see if I can do that. Otherwise, you can see my whole screen. Just a second. See, the option to present only one app.
Now the slide is visible, sir.
Okay. Can you approve my joining? I'm trying from my mobile phone as well. I'm going to have two logins.
Okay, sir. Varsha?
Yes, ma'am.
Please allow sir to join another.
Yeah, I've got in here. Okay.
And Kritika, ma'am, you can proceed, ma'am.
Okay.
All right.
Sir, shall I start?
Go ahead.
Thank you, sir. A warm good evening to one and all. On behalf of Hindustan College of Engineering and Technology and on behalf of Department of Science and Humanities, I extend a very warm welcome to all the active participants on the first day of National Visual FDP on Diversity of Mathematics. I would like to welcome our HOD ma'am, Dr. K.P. Uma, who gave a good support to arrange this FDP. I invite our faculty coordinator, Dr. R. Sima and Mrs. B. Kausalya to the full support. And finally, I welcome our student coordinator, Ms. Varsha. I'm very glad to introduce our speaker, Dr. Ashwin Ganeshan, who is going to present on the topic Distributed Algorithms for QoS in Wireless Networks. He received his bachelor's degree from Marquette University. In 1998, majoring in electrical and computer engineering and with a second major in mathematics and a minor in computer science. He was a core engineer at Eaton Corporation. During 1995 to 1997, he received master's degree in electrical engineering from the University of Wisconsin at Madison. He was a research and teaching assistant at the University of Wisconsin at Madison during 1998 to 2001 and 2004 to 2008, and a faculty member in various reputed engineering institutions. Now, he is an associate professor at the International School of Engineering, Mumbai, Maharashtra. His research areas include distributed algorithms, graphs and algorithms in communication networks, discrete mathematics and graph theory, interconnection networks, and applied combinatorics. He published 15 papers in various reputed journals, and he presented 9 papers in conferences. With this introduction, I hand over the session to you, sir. The floor is yours.
Thank you very much, Professor Kritika, for the kind introduction. So, I'll be presenting today I'll be talking today about this topic, distributed algorithms for QoS in wireless networks. I hope you can see my slides there. I have the outline here in front of me.
Yes, sir.
Yeah, okay, good. So basically, I have a tablet that I'm looking at which has the slides. And so that's at my desk. And I have the camera at my side facing me from the side. So I'm not going to be looking directly into the camera when I give the talk. I'll be looking at the side. But if you have any questions, you can feel free to convey that. And we'll have, I think this is about almost a 1 hour session. I'll try to finish in about 15 minutes, and then we can have a question and answer session at the end. And I'll also, discuss some open problems. So this is basically my research in the area of discrete applied mathematics. And within applications of discrete mathematics, my favorite area is applications of combinatorics, and especially applications of graphs and hypergraphs. So in the first part of the course, I'll be talking about how conflict graphs are used to model the interference in wireless networks. And I'll give some distributed algorithms for the problem of flow admission control in wireless networks. And in the second part of my talk, I don't know if I'll have time to get to it, I'll talk about the hypergraph interference models, and I'll look at the worst case performance of some scheduling algorithms that use this particular hypergraph interference model. And then at the end, I'll have some open problems. Okay, so here's the problem that we'll be discussing today. So consider a wireless network which is modeled by a simple undirected graph G, which has vertex set V and link set L. So G is called the network graph because it's the graph that represents some network. Okay. V here, the set of vertices, is the vertex set of the graph. And each link Li corresponds to a pair of nodes within communication radius of each other. So you can imagine a bunch of dots, a bunch of vertices on the Euclidean plane, where if two vertices are very close to each other, if they're within communication radius of each other, then those two vertices are joined by an edge. Otherwise, the two vertices are not joined by an edge. So you get the set of links L in that manner. Now the problem is that communication cannot take place across all the links simultaneously due to wireless interference. And which links interfere with which other links is modeled by a conflict graph GC. The vertex set of the conflict graph is L. So notice that the vertex set L is the same as the link set L of the network graph. Okay? And two vertices, Li and Lj, form an edge in the conflict graph if and only if those two links interfere with each other due to wireless interference. So exactly which links of the network graph G will be made adjacent vertices in the conflict graph depends on the particular situation. We'll see at least a couple of different situations, but it really depends on the context. There's no one way to go about it. It depends on what problem you're interested in solving. But this notion of defining a conflict graph that captures the competition between entities in a network that are competing for resources is not really a new concept. It's really what graph coloring it's really what graph coloring applications all do generally. Gregory Chaitin, for example, looked at the conflict graph model for when you design compilers during the register allocation phase. you want to decide which variables should be allocated which registers, and there you construct a conflict graph. And Jane actually and his co-authors in 2003 looked at the conflict graph specifically in the context of wireless networks. So we actually have two different graphs here that we'll be looking at throughout the rest of this talk. One is the network graph G, and the other is the conflict graph GC. Okay? Okay, so let's look at a couple of examples of the conflict graph. Here I have a CDMA system. A CDMA system is sometimes, it's another word for code division multiple access. So it's basically a particular, so many cell phones, for example, the cell phones that are designed by the company Qualcomm use this particular technology. And in that particular technology, all users in the network can transmit at the same time and the same place, and that wouldn't cause any interference because they all use different spreading codes. So if you look at this particular network right here on the left, you have these different wireless links, and if you take, for example, so we're going to look specifically at the CDMA system where each node is equipped with only one transceiver. Okay, and because this node right here is equipped with only one transceiver, so let's say you have this node right here, it's only equipped with one transceiver. Nodes A and D interfere with each other. So nodes A here, links A and D interfere with each other because the node that's right here has only one transceiver, so it can either send or receive, it can either transmit or receive on any one of the links A or D at any given time, but not both. And that's why the links A and D are made adjacent vertices in the conflict graph. Okay. If you look at, for example, another set of links, let's say we look at links A, E, and G. These three links have no endpoints in common. Okay, A and E, as you can see, A here and E here, they have no endpoints in common. The endpoints of A are this node and this node. So they have no endpoints in common, and the endpoints of E also are different from the endpoints of A. So they don't actually interfere with each other. That's why what you see here is that the nodes A and E have no edges between them. You can see that they have no edges between them. Similarly, G as well is not going to be interfering with A or E, and so you can see there's no edge between G and A or G and E. More specifically, as long as the set of links in the network graph is a matching, the set of vertices, the set of corresponding vertices in the conflict graph is an independent set. So you can see here that the set of vertices A, E, and G is an independent set in the conflict graph. Let me make that clear. So those set of three links is a matching in the network graph. A matching is a set of edges such that no two of the edges have an endpoint in common, and they form an independent set in the conflict graph. There will be no edges at all between any pair of vertices in an independent set, right? Okay. So this is an example of a network that you see on the left, and then the conflict graph that you see on the right, which captures which links in the network interfere with each other with this adjacency relationship. Here's another example of a network, which is a Bluetooth network. So in a Bluetooth network, for example, you have a master node which communicates with 4 slave nodes, and they communicate in like a time division manner, which means links L1, L2, L3, and L4 all interfere with each other. Okay, they can't all be active at the same time. They all must take turns transmitting at different times. So those 4 vertices you can see here form a complete graph because every one of them interfere with each other. L1 and L3, for example, interfere at node M. Okay, so you get the complete graph. So that's another example of how the conflict graph is constructed from the network graph. Here's another example of how the conflict graph can be constructed from the network graph. So here on the left, we see a network G, and it has several nodes and several and 5 links. And what you see, for example, is that links L1 and L3. Okay, so L1 is there and L3 is there. So it turns out that do they interfere with each other or not? That's the question. In other words, should L1 and L3 be made adjacent vertices in the conflict graph? That's the question. So in the IEEE 802.11 MAC protocol, when a flow AB is active, all the other flows incident to any neighbor of A or B must be inactive. So when node A transmits to node B, at that time, node B would send an acknowledgement back to A, and that acknowledgement would also reach node D. And because that acknowledgement also reaches node D actually cannot receive any information from node E at the same time. So basically, when the communication between nodes A and B is taking place, there can be no communication between D and E. In other words, the distance between the edge AB and the edge DE is exactly 1. And that's distance 1 is enough to cause interference. Okay, and so we make those 2 particular links, L1 and L3, to be adjacent in the conflict graph. On the other hand, if you take the links L1 and let's say L4, the distance between the links L1 and L4, as you can see here, is its 2 edges, and that distance of 2 edges is large enough that L1 and L4 do not cause any interference with each other. So links L1 and L4, you can see, are not adjacent in the conflict graph. Okay? And so this is an example of what you would call the 2-hop interference model, because 2 links can be transmitting at the same time. They can be active at the same time if and only if the distance in the graph G between those 2 links is at least 2. Okay? Now, this model of interference is sometimes called the secondary interference model. But in the rest of this talk, we're going to be focusing on the primary interference model. And that's the model we saw right here, where 2 edges in the network graph or adjacent vertices in the conflict graph, whenever the 2 edges have an endpoint in common. Okay? Whenever the 2 edges are incident to a common node. And so we're going to be looking at this primary interference model in the rest of this talk, at least for the next few slides. Later on, I'll get to more general interference models if I have the time. At least for the next few slides, I'm going to assume here that the network graph is going to have this kind of an interference called primary interference. In fact, you might actually know, if you've studied this in graph theory before, that the conflict graph is called the line graph of G. Okay? The conflict graph is sometimes called the line graph of G in this particular case. And that's in this particular case of the primary interference model. Okay, So let's look at the quality of service requirements and what they are. So basically, in many wireless applications, you have applications like real-time video, like video conferencing, like we're doing right now, and voice over IP, where these are real-time applications which are using the standard internet for transmitting data, but the standard internet does not make any guarantees for the delivery of data. When you use the standard internet, the packets that are transmitted need not arrive in the same order in which they were sent, and they can also sometimes get lost. So applications will often make a demand ahead of time and reserve bandwidth ahead of time about what based on their quality of service requirements. So for example, real-time video would have a higher quality of service requirement than real-time audio. And they both of these would have different kinds of requirements than let's say FTP. So in FTP, all the bits must arrive without being corrupted. In audio, even if some of the bits are corrupted, it's fine, but you cannot tolerate delay. Whereas in FTP, you can tolerate delay, but the bits must not be corrupted. So every application has its own set of requirements in terms of either the delay or maybe the reliability of the data, or maybe the throughput. And in this particular talk, I'm going to be looking at requirements which are specified in terms of throughput or the data rate. So basically, every link will L will make a demand to transmit data at a rate of f of L bits per second. So if it's audio, the demand f of L would be higher than if it's for video. So every link or edge in the network graph makes a demand to transmit information at a certain data rate, and if the total bandwidth of the shared wireless medium is c bits per second, then what you can do is divide f of L by c, and what you get is the requirement in terms the requirement tau of L, and that tells you tau of L represents the fraction of each unit of time that the particular link L has to be active for. So for example, if let's say that C was 2 megabits per second. So if that's the total bandwidth of the entire shared wireless medium, and let's say that f of L was, let's say, 1 megabit per second, then that would imply that tau of L is 0.5. It's the ratio of f of L to C. So basically that means that the link L can transmit for 50% of every unit of time. And if it did that, if it transmitted at 2 megabits per second for 50% of every unit of time, then it would achieve its requirement of 1 megabit per second if they have an endpoint in common. So links L1 and L2 interfere with each other because they have this endpoint B in common. Okay? And links L1 and L3 don't interfere with each other because they have no endpoints in common, because L1 and L3 together form a matching in the network graph. So what you're given is this graph G, and for every node, you're also given the data rate requirement. So for example, L1 wants to transmit 0.4 C bits per second, L2 wants to transmit at 0.4 C bits per second, and so on. So every one of the 6 links has a demand to transmit at a certain data rate. And the question that we have is a yes or no question. So given this particular input, the question we're going to ask is it feasible or not? Determine whether the given flow rates are feasible. So that's the question that we want to answer. It's a yes-no question. And the answer to this question is yes. These flow rates are feasible. So what you could do is take up your 1 unit of time and split it into 5 parts. So in the first part, you're going to have L1 and L3 being active. So So L1 and L3 can transmit at the same time, and they will transmit during the first 20% of every unit of time. Similarly, L2 and L4 also form a matching. What you can see here is, for example, that L4, L1, and L6 is active at the same time during the fourth time slot. And sure enough, you can see here that L1, L4, and L6 form a matching. Okay? They form a matching in the network graph, so they can be active at the same time. And what you can now see here is that if L1 is active for 20% during the first 20% of every time slot, and if L1 is active for another 20% during the fourth 20% of every time slot, then together L1, and if each time L1 is active, it transmits at full blast of C bits per second, then you get 0.2 C here and another 0.2 C here, and you've achieved your data rate of 0.4 C bits per second. So this demand of 0.4 C is feasible. And you can similarly see that all the other links' demands are also satisfied. Okay? And therefore, the answer to the question, are these flow rates feasible, is yes, they are feasible. And in fact, here's a feasible schedule. It's basically the schedule that you have right here. And so this is the general problem that we'll consider. We'll simplify the problem a little bit, just get rid of one of the variables, namely the variable C. We can actually divide all of these link demands by C and express the demand as just the fraction 0.4. And so that's what we're going to do in the next slide here. So we're given again the network graph G, and we're assuming it's again the primary interference model. And we're given the fraction of time tau of L for each link L. So you see only the number 0.4 is mentioned, not 0.4C. And the question is, given this network graph along with the link demands right here, you have to determine whether those demands are satisfiable. This is a yes/no question. And the answer is yes, because here is a feasible schedule. L1 is active for 20% plus 20%, which is 40%, so that satisfies the demand of 0.4. Similarly, L6 actually only needs to be active for 0.1, but it's actually active for 0.2 here, so that's satisfied as well. And so we have a feasible schedule. The requirement in a feasible schedule is that the set of links that are active at any given time must be an independent set in the conflict graph, or equivalently, they must form a matching in the network graph. So you can see that L3 and L5, which is basically this link right here and this link here, that is a matching in the network graph. Right? L3 and L5 is a matching in the network graph. Similarly, L2 here and L5 here is also a matching, and so those two links can be active at the same time as well. And so this is a problem. This is a yes/no problem, and it's a very interesting graph theory problem, applied graph theory problem, I should say. Okay, so one thing that you might be tempted to do is say, well, if I'm given a graph like I'm given right here, right? I'm given the graph G, and I'm also given tau. Okay, so I'm given G and tau. G is the graph, and tau is the demand for every L, right? That's what this says right here. The tau of L is the demand for every link L. So you're given G and tau. That's what you're given. It might be tempting to say that as long as the demands of all the links which are incident to any particular vertex is at most 1, then the demand vector is feasible. So for example, if you look at node B, L1 and L2 interfere with each other. And if you look at their demands, L1 and L2, they sum up to 0.8, right? 0.4 plus 0.4 is 0.8, which is less than or equal to 1, which means you can always, go ahead, you would think, ahead and say, all right, I'll just go ahead and schedule, you know, L1 here and then L2 here at different times. And then L2, L3, and L6. Okay, let's look at L2, L3, and L6. So L2, L3, and L6, they interfere with each other. They should be scheduled at different times. Well, that's not a problem. I mean, you have L2 already taken care of. L3 should be different from L2. So you can put L3 at the same time as L1. That's not a problem. And then L6, you can go ahead and schedule right here, and so on. Okay, it turns out, so I mean, you might be tempted to think that if the sum of the demands of all the lengths incident to each vertex is at most 1, then the demand vector is feasible. You can define the degree of the vertex C to be the sum of the demands of all the lengths incident to vertex C. So that means that the degree of C is 0.4 plus 0.4, right? 0.4 plus 0.4 plus 0.1, that's 0.9. But actually, so the demands of all the lengths is less than or equal to 1 in this case. Is that a sufficient condition for the answer to be yes? Is that a sufficient condition for the demand vector to be feasible? Well, it turns out it's not. And here's why the degree condition is not sufficient for feasibility. For those of you who have studied graph coloring, and especially perfect graphs, you know that the odd cycle graphs are the simplest non-trivial examples. I mean, the odd cycle graphs, require, the edge coloring number of the odd cycle graphs is more than the maximum degree of a vertex, or can be more than the maximum degree of a vertex. And that's the problem here. The problem is that the maximum size of a matching in this graph, so in this particular graph, you can see that the degree of every vertex is 1. So vertex B, for example, has 2 links L1 and L2 which interfere with each other incident to it. And the sum of the demands for L1 and L2 is 0.5 plus 0.5, which is 1. So it appears that you should be able to satisfy the demands of all the 5 links because the degree of every vertex is at most 1. But it turns out that can't be done. And here's a short proof. When any given time, so you have this time slot from 0 to 1, and during any given time you have at most 2 links active because the maximum size of a matching in G is 2. The maximum size of a matching in G is 2. Actually, when I write on my tablet, it takes actually sometimes a couple of seconds for the writing to show up on my laptop here. So I'm assuming that the same delay, or maybe even a larger delay, occurs on the other side as well. So this is an example where if I have a quality of service requirement that the delay must be at most 1 second, then that delay is not met by whatever infrastructure I'm using. Okay, so similarly, of course, in my talk here, the quality of service requirement is not a delay; it's a bandwidth or a data rate requirement. But anyways, sometimes I'll just look at my laptop here or the webcam and just make sure the writing is showing up because there's sometimes a delay here. Okay. So you can see here that L1 and L2 cannot be active at the same time, but L1 and L3 can be. Okay, but at any given time instant, at most 2 links can be active because the largest size of a matching in G is only 2, right? It's only 2, and so you can only have 2 links being active, but the sum of these 5 demands is 2.5. Okay, the sum of these 5 demands is 2.5, but at any given time, you can have at most 2 links being active, and therefore, the total amount of time that it would take to satisfy a total demand of 2.5 is at least 1.25. Okay, so we need to extend this to go to at least 1.25. We actually cannot satisfy all these 5 links demands within 1 unit of time. Again, I've written something on my tablet which has not yet appeared even in my tablet screen. Wait. All right. So I think the best thing to do then is to use this pen. So I think this, so this 1 is not enough. You need 1.25 at least, because just satisfying the demands of these 5 links will take at least that much time. So are you able to hear me clearly, Professor Kritika? Is everything clear so far? Am I audible?
You're audible, sir.
Okay, very good. Okay. There was a delay of about 5 seconds from the time I wrote this 1.25 on my tablet to the time it showed up on the screen. So I just want to make sure it's okay on the other side. All right, good. All right, so let's continue here. So what you see here is that we need something better than the degree condition. So I'm going to state the admission control problem formally here. So we're given a network graph G and a conflict graph GC, and we're given a link demand vector tau. And let I of GC denote the set of all independent sets of GC. A schedule is a map from the set of all independent set of GC to all the negative real numbers. So it assigns to every independent set a time duration T of I that specifies the fraction of every unit of time that independent set I will be active for. So that's a schedule. Now, if you have such a schedule T, then the total duration that the link L is active is basically the sum of the time durations T of I over all the links I which contain a particular link L. So that sum is going to tell you how much of, it's going to tell you the fraction of every unit of time that link L in particular will be active for. And the total duration of the schedule is the sum of the durations assigned to all the independent sets. And a demand vector tau is feasible if there exists a schedule of duration at most 1 such that each link L is active for duration at least tau of L in that particular schedule. And the admission control problem is stated formally as follows. Given G and which is the network graph, and then GC, which, and you need to know the conflict graph GC because you need to know which pair of links interfere with each other. And so basically adjacent vertices in the conflict graph correspond to a pair of links which interfere with each other. So given G, GC, and the link demand vector tau, determine whether tau is feasible. That's basically the problem that we're going to be looking at. So just to kind of give you an overview of this problem in the terminology that you might be more familiar with. So probably those of you who have looked at graph theory or graph optimization problems might have come across mixed integer linear programming formulations of various graph optimization problems. For example, finding the chromatic number of a graph is a mixed integer linear programming problem. And then if you relax the condition that the variables have to be integers, then you get the fractional variance, the fractional chromatic number of the graph, and the problem we're looking at is very similar to that. So the independent set polytope is the convex hull of the characteristic vectors of the independent sets of the graph GC. So if you actually take, the sum, if you take all convex combinations of all the characteristic vectors of the independent sets of the conflict graph, then you basically get this independent set polytope, and basically you can think of it as independent set II is assigned time duration lambda I, and since the sum of lambda i's should be 1, so the lambda i's are non-negative and sum to 1, any vector that you get by taking the sum is going to correspond to a demand vector which is feasible, meaning which can be satisfied by a schedule of duration at most 1. So Pi of GC is exactly the set of all demand vectors which are feasible. Now let B be the vertex independent set incidence matrix of the conflict graph. So given a conflict graph GC, and given a linked demand vector tau, the fractional chromatic number of the weighted conflict graph GC comma tau is defined to be the minimum of 1 transpose x subject to bx at least tau and x at least 0. This is basically, if you had imposed the additional condition that x has to be an integer vector, then you would have gotten the chromatic number of the weighted graph. Okay, I'm assuming here, of course, that tau would be integral as well in that case. But anyway, the point is that we're now dropping the constraints that x be an integer, and so the compared to when you're calculating the chromatic number, when you're calculating the fractional chromatic number, this search space, the feasible set, is going to be larger because you've dropped the integer constraints, and therefore the minimum value would be less than or equal to what you had earlier, and that's why the fractional chromatic number is less than or equal to the chromatic number. Okay. So the minimum duration of a schedule satisfying tau, you can think about it, but it's basically exactly the fractional chromatic number of the weighted conflict graph. So basically what that means is that we have equivalent definitions for feasibility. Given a conflict graph GC and a linked demand vector tau, determining whether tau is feasible is the same as determining whether or not tau is in the independent set polytope of the conflict graph, and that's equivalent to determining whether or not the fractional chromatic number of the weighted graph GC comma tau is less than or equal to 1. So we started with a quality of service requirements problem in wireless networks, okay, with a problem of QoS in wireless networks. And we wanted to know if a given set of flow rates is feasible or not. So given this particular weighted graph, answer the yes/no question, and we saw that that's equivalent to determining whether or not the fractional chromatic number is less than or equal to 1. So this is all just to give a background, because I want to go very slow in the beginning to make sure everyone's on the same page. I'm now going to start going a little bit more quickly so that I can mention the new results and then the open problems. Okay. If I went really fast in the beginning, I'm not sure. I mean, I was told the audience has research scholars as well as faculty. I wanted to go slow in the beginning, but I'm going to speed things up. And for those of you who are interested, you can always go to my webpage or go to archive and go through the publications in detail to get the results that are there. So basically, it turns out that for the very particular case where the conflict graph is the line graph, you want to find the fractional chromatic index of the edge-weighted graph, and you want to determine whether or not that's less than or equal to 1. It turns out that these problems of admission control as well as scheduling can be solved in strongly polynomial time. The problem is that that requires knowing the entire graph, and we're going to be looking at problems where each node in the network will make a decision based only on its local neighborhood, because the cost of communicating the information about the entire global topology to a single centralized node is very expensive. And so if each node has information only up to d hops away, or maybe often d is 1 in the later part of this talk, d is 1, then what are the best decisions that can be made? So you can define the worst case performance. So it turns out that if you're given any sufficient condition for feasibility, you can define the set of all link demand vectors which satisfy that sufficient condition. And because that's a sufficient condition, that set PS would be a subset of the independent set polytope. And the worst case performance of the sufficient condition S is the smallest scaling factor alpha, which will convert the sufficient condition into a necessary condition, meaning it's the smallest alpha such that Pi is a subset of alpha PS. So we're looking at distance d-distributed algorithms where basically suppose that you have this big network graph right here. The one-hop neighborhood centered at node A is basically you take all the nodes which are within distance 1 from A, and that would be the one-hop neighborhood. So it would be G, A, comma 1. Okay, the two-hop neighborhood would be you take node A and you take all the nodes which are at distance at most 2 from A, as well as all the links induced by those vertices, and you basically get this two-hop neighborhood. Okay, that's G, A, comma 2. So G, A, comma 2 is the subgraph of G induced by the two-hop neighborhood centered at A. The distance d-distributed algorithm in the form of a pseudocode. So the sufficient condition which talked about this value and this value is converted into the form of a pseudocode. Again, you can look at my paper to get this in more detail. Yeah, so basically another distance 1 distributed algorithm is called the row constraints, and it's actually a generalization of the greedy graph coloring algorithm that you might have seen, where the number of colors needed to color the vertices of the graph is at most 1. So you have that 1 plus delta is less than or equal to, let's say, k. So you know that a graph is k colorable. K colors are sufficient to color the vertices of a graph if 1 plus delta is at most k. And that's really what we're saying. 1 unit of time is enough for the demands of all the vertices of the conflict graph. If the demand of every vertex tau plus the demand of all the neighbors, the demand of some particular vertex L plus the demand of all the neighbors of L is at most 1. And what I showed is that the worst case performance of that particular sufficient condition is at most some quantity called the induced star number of a graph. So that's basically this result, which was published in Applied Mathematics Letters in 2010. And I showed that under something called the protocol interference model, this is again in the same paper, that the conflict graph contains a claw. So a claw is basically an induced subgraph isomorphic to K13. So it's a center with 3 vertices. That's what a claw is. And the problem with a claw is that if a graph has a claw, then many of the polynomial time algorithms which are known for claw-free graphs cannot be applied to color the conflict graph, or to do various other resource allocation problems on the conflict graph. So I basically showed that for a very particular kind of a network called a line network, and for a very particular kind of an interference model called the protocol interference model, the conflict graph contains a claw. But I also showed that, you know, it'll never contain a K14. So GC will never contain an induced subgraph isomorphic to a K14. It'll only contain a K13 at the most, which is kind of good in a way because you know, that means that the worst case that in the worst case, the performance of the row constraint, that's one particular distributed algorithm, is away from that of an optimal centralized algorithm by a factor of at most 3. And this notion of interference can be generalized to hypergraphs. I just have another 3-4 minutes, so let me just tell you briefly the hypergraph interference model. So basically you have there are many examples where the interference might be modeled with a hypergraph. So you can have a network with, let's say, 3 links, L1, L2, and L3. And it's quite possible that, you know, any 2 of these links, L1 and L2, so if L1 and L2 are simultaneously active, that's okay. If L2 and L3 are simultaneously active, that's okay. If L1 and L3 are simultaneously active, that's okay. So basically, any 2 of the 3 links can be simultaneously active, and if that happens, the interference is tolerable. But if all 3 of them are simultaneously active, the interference is too much, and that's not tolerable. So you would define then E to be L1, L2, L3. It's a minimal forbidden subsets of links. Okay, so it's minimal because any proper subset of E can be active at the same time. It's not forbidden. So any proper subset of E is not forbidden, but E is forbidden. And so you collect in a network all such minimal forbidden subsets of links, and they form the edges of your hypergraph. And there are many problems where you need these more general interference models, and often they're more realistic approximations as well than graph theoretic models. So one of my results is you can define the notion of a fractional chromatic number for a hypergraph in the same manner as we did for a graph. And one of my results is basically the following. The worst case performance of the some particular sufficient condition for admission control, I call that worst case performance beta of H. It equals sigma of H. So this generalizes the notion of the induced star number that I had shown earlier. So we don't have time to get into this, but I just want to say here that there are many directions here for further research. So if you like graph theory, if you like hypergraphs and so on, there are many problems here which are worth investigating. I would suggest that if you want to look at open problems, that you start with this particular reference. So I've posted a preprint just about a little over a month ago on arXiv at that particular URL, and it talks about some thing called the distance D distributed algorithm for the K-hop interference model. So in the K-hop interference model, you have something called a K-separated matching. So a subset of edges is a K-separated matching if the distance in G between any 2 edges of F or in that subset is at least K. So one separated matching is what we've been looking at. It's called a matching. So the distance between any 2 edges of a matching is at least 1. But you can be more restrictive and say, I want a subset of edges such that any 2 edges in the subset are apart by a distance of at least 2 or 3 or K. So these are stronger models of interference. This means that the capacity or throughput of such a system is going to be, lesser than otherwise. And there's a lot of open problems there. So you can look at this paper that I have right here and look at it. So I'm basically pretty much out of time here. Professor Kritika, is there a method here for students to ask questions?
Yes, a few participants have joined in the Google Meet to ask questions.
Okay. Let me just go here to chat.
Participants, please ask their questions.
Okay, great. So there was one person, Mira, who asked if there are open questions in the area. Yeah, that's an excellent point. So I would suggest that you note down here this particular URL. And, one of the things, for example, is I look at the worst case performance of the distance to distributed algorithm for, so this particular paper considers d equals 1 and k equals 2. And there's, in fact, I look at c for k plus 2. So I look at the case where the network graph G is the cycle of even length. In fact, not just a cycle of even length. It's the cycle of length 4k plus 2 for any integer k, where k is at least 2. And well, I should be clear actually that this k is different from that k. So why don't I use some other variable like L? Okay. Yeah. So basically, the case where you choose your cycles to be of other lengths, so instead of the cycle length being 2 mod 4, if it's 1 mod 4, 3 mod 4, or 0 mod 4, those haven't been done. I think the same technique should be applicable, but I've just left it open because I think other people should probably they would be very interested in this and they can work on it. So you can feel free to download it. This paper is still under review, but it's on the public domain, so you can feel free to download this and extend the results as you wish. Besides this, there are extensions to weighted conflict graphs and hypergraphs, and I would suggest just looking at the references in this particular paper. The references in this paper are quite exhaustive and complete, so I think you would get many other directions by looking at the references as well. Are there any other questions besides that?
Participants, kindly post your questions in the chat box.
Yeah, okay. So I mean, if you can feel free to email me. I think the website is just this one. I think you can just go to my homepage and go to the publications page from my homepage and get the papers from there if you want to see the remaining papers as well. So there's no further questions. Thank you very much for attending. I hope you find it interesting. Feel free to contact me if you have any questions.
Thank you, sir. Thank you so much. Now I welcome Dr. Rod Purnima to give vote of thanks.
Thank you, Kritika. A very good evening to one and all. On behalf of the management of Hindustan College of Engineering and Technology, Department of Mathematics, and my own behalf, it gives me an immense pleasure to deliver the vote of thanks for this 2-day National Faculty Development Program on Diversity of Mathematics. Today's topic is distributed algorithms for QoS in wireless networks. So let me first of all start by giving glory to the Almighty God for making today's FDP a resounding success. First and foremost, I thank our chief guest, Dr. Ashwin Ganeshan, Associate Professor, International School of Engineering, Mumbai, Maharashtra, who despite his busy schedule has found time to grace this national FDP. Thank you, sir. Your presentation clears about the QoS in wireless networks. Thank you very much, sir. I express my heartfelt thanks. Yeah, thank you, sir. I express my heartfelt thanks to our head of the department, Dr. K.P. Uma, for her constant support and guidance. Thank you, ma'am. I thank the other coordinators, Mrs. B. Kausalya and Ms. M. Kritika, for their support to make this national FDP a successful one. Thank you, friends. I thank all the participants for their effective participation and patience listening. Thank you all. Last but not least, I thank the student coordinator, Ms. Shri Varsha, for her technical support. Thank you, Varsha.
Thank you, ma'am.
Once again, I thank you all. Thank you.
Sir Aswin sir, I am Uma, head of the department. Thank you very much, sir. It was very much informative to us. Thank you very much, sir. Thank you for your acceptance.